Hi, this is Mark Weitzman. Welcome back to my channel, Theoretical Physics with Mark Weitzman on YouTube. I want to finish the last video, part 3, on lesson 8. Lesson 8, um, the path integral for free field theory. Um, so now we want to evaluate time ordered products of field operators using the free field theory path integral. And so we remember that we've established one formula for z0j e to the I over 2, the integral of d4x prime jx Feynman propagator jx prime. And we're trying to calculate time ordered product. Time ordered products of field operators between the vacuum. And this is given by 1 over I. Same thing as for the harmonic oscillator that we did previously. Del jx1. These are functional derivatives applied to z0j, and then we evaluate them at j equals 0. And okay, so this we've established. Now let's do the 2-point function. So let's calculate 1 over I del jx1, 1 over I del jx2, z0j, evaluated at j equals 0. And remember, for functional derivatives, it's simply that del jy del jx is equal to delta x minus y. Same thing, this is just the continuous version of the partial of xk with respect to xj is equal to del kj. Okay. So continuing on with this, we get 1 over I del jx1 the integral of d4 x prime delta x2 minus x prime j x prime z0j, all of this evaluated at j equals 0. So what I did there, I kind of like skipped a step. I skipped the step here. So when we take the functional derivative of the z0j with respect to jx2, we have an exponential. So we're always going to get back that exponential. So that gives us the factor of z0j here. Now, when we take del jx2, we have two sources in there, but we also have a half here. It's easy to see that you get the same one. But when you take like del jx2, you get a delta function, x minus x2. When you integrate over x just becomes x2, so that's why we get this x2 over here. We keep the x prime, we keep the jx prime. We're always doing 1 over I, so that cancels the I there. And the two factors is canceled because while I did jx, I could also do jx prime, and the Feynman propagator is symmetric, so you always get the same thing. Okay, and you don't take the, sorry. You don't take the derivative, you don't set j equals 0 until you finish the whole process. So this is equal to, now we get the next term. Now we can take the derivative of this thing in brackets, that's one possibility, or we can do the z0j again. So let's first take the derivative in the brackets. So now I get 1 over I so when I take del jx1 with the jx prime, I get a delta function, delta x prime minus x1. When I integrate over x prime, I just get x1. So I'm going to get 1 over I delta x2 minus x1. Okay, that's good. And then I'm going to get the next term, which is going to be equal to what we had there, because we're going to d4x prime and now we're going to do 1 over I del jx1 del z0j. Now when we in this term over here, and the whole thing is going to be evaluated at j equals 0. This is going to bring down more factors, but when we set j equals 0, this is going to go to 0. So it doesn't matter. We don't have to take this actual derivative here because this term just gets wiped out. So we're left with 1 over I del x2 minus x1. Nice result. Okay. So now problem 8.4 in Sugnicki is basically says let's do the same thing except just do it by substituting in field operators and everything, because we're doing the free field, so we're only working with free fields. So let's say we have, so what we want to evaluate is 0, time ordered phi x1, phi x2, 0. Now let's work with the case where t1 is greater than t2. So if t1 is greater than T2, then they're already time ordered. So it's just 0, phi x1, phi x2. And we can easily evaluate this because we have formulas previously that we've derived for our field operators. So we're going to get the integral of dk1 tilde, dk2 tilde, 0. We have a k1 e to the I k1 x1 plus a dagger k1 e to the minus I k1 dot x1. And that factor is times a k2 e to the I k2 times x2 plus a dagger k2 e to the minus I k2 dot x2. And then we have the sandwich in the vacuum. Why won't this move up? Okay, now so this is easy to handle. First of all, the a dagger kills the vacuum on the left side, and the a kills, in the second term, kills the vacuum on the right side. So this is just equal to the integral of dk1 tilde, dk2 tilde, 0, ak1, a dagger, k2, 0, e to the I, k1 x1 minus k2 x2. Okay, and continuing, notice that now we use the commutation relations we have with the creation operators, and we have a funny measure, but we've already done all this. So the integral d tilde k1, d tilde k2, we get 2 pi cubed, 2 omega, doesn't matter whether we make it k2 or k1, del 3, k1 minus k2, e to the I, k1 x1 minus k2 x2. Okay, well, this 2 pi cubed 2 omega k2 kills the relativistic part of the dk2. So this just becomes the integral of d tilde k1 dk2 del 3 k1 minus k2 e to the I k1 x1 minus k2 x2 . So now the k2 integral becomes very easy, and we have just the integral dk1 tilde e to the I k1 x1 minus x2, because we said k1 equal k2. So this is the first term of equation 8.13, and using the other time order, remember we used T1 greater than T2. If we look at T1 less than T2, we would get the second term. We would get the second term. Okay, so let's go back. That just confirms what we already knew, that we could do it. That's sort of like the canonical approach. In general, if we have an odd number of fees, then the zero time ordered fee dot dot fee 0 is equal to 0. This is easy to see. You can see it easily with the creation and annihilation operators. And if we have an even number, they have to be paired up. So we get, for instance, if we had the 4-point function, this is going to be equal to 1 over I squared. Then 2 Feynman propagators with being paired up at all different points. There's going to be 3 possibilities. And you can see how this is starting to sort of get to scattering. Imagine we have a particle at x1 and a particle at x2, and for the 2-point function they just propagate. So this is just basically I'm leaving out the factors of I. But now if we have x1, x2, x3, x4, we can have them go, we can x1 to x2 and x3 to x4, and we'll get the first term here. Or we could have them go this way, x1, x3, x2, x4, or we could have x1 go to x4, and there's no interaction here or anything. x3 goes to x2. So you can see how sort of we'll be using this in 2-particle goes to 2-particle elastic scattering. The general formula is just this is just going to be equal to 1 over I to the n, the sum over pairings, del xi1 minus xi2 dot 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 del xi2n minus 1 minus xi2n. Okay, so that's it for this video. And then next week we'll go in lesson 9. We'll start with interacting field theories. Thank you very much for watching. I'll see you next time. Bye-bye.